Well, let's take a look at the problems on the 6.1 Achieve assignment discussing area between curves. This first problem is one of theirs where they're just trying to make sure we get the algebraic basis required for some of the problems in the section. So you'll see it says in this multi-step activity, you will review finding intersections between two graphs, and that's going to be this first problem, finding the intersection values of two graphs. So they give us a function f of x, which is a linear function, negative x plus 35, and a function g of x, which is the group x minus 2 squared plus 3.5. Now I'm supposed to find the solutions and round to 4 decimal places. Okay, no problem. I set one function equal to the other. I know that that group squared is of going to be no help whatsoever, so I go ahead and square it out in this first step, and I say x minus 2 quantity squared is just going to be x squared minus 4x, and then it would be plus 4, but I also had another plus 3.5 over here, so instead of x squared minus 4x plus 4, I said x squared minus 4x plus 7.5. Now, I know I needed to set this equal to 0 to try to solve it, so if I had this set equal to negative x plus 35, then I moved everything to that right-hand side, and I said, well, then I have an x squared. I'd have minus 4x, and I'd have to add x to both sides to get minus 3x. I had a 7.5. I'm subtracting 35 from each side. Well, that gives me minus 27.5. So then there's a bunch of different ways you could solve out this. I just went ahead and did it the easiest way that I could show on paper, just using the quadratic formula. So in order to solve out when this quadratic is equal to 0, I said x is equal to negative b, positive 3, plus or minus the square root of b squared, positive 9, minus 4 times a, which is 1, times c, which is a negative 27.5. Take all of that and divide it by 2 times a, 2 times 1. The inside of the square root simplified to be 119. That doesn't simplify as a perfect square, so for my final answer, I just said 3 plus the root of 119 divided by 2, and then 3 minus the root of 119 divided by 2. When I did each of those, you'll see the answers I got down here, the 6.9544, and it specifically asked me to round to 4 decimal places. A lot of times it'll ask for an exact answer, so I'm surprised it didn't want the 3 plus the root of 119 over 2, and then the 3 minus the root of 119 over 2. But we'll follow the directions and do 4 decimal places, so 6.9544 for one x value, and the other negative 3.9544 should be what they're looking for. Check that, and it likes it. Their next problem is one of these where it's just going to do a media, and it's going to talk about how the area between two curves, if you have a top function and a bottom function, it's just the top minus the bottom function, where the width is going to be the change of x, since that's the bottom, the width of each rectangle you would use to approximate this area. So they're just going to go in and explain how that is, similar to what I did on our video introduction for this section. It's probably worth a watch there. I'll just hit play and pause to get credit for it and move on. So now it's giving me an application of that one. And this, it could be, well, it probably is one of the harder problems in this section, especially for it to be so early on. It's asking us to find the area of the shaded region formed by the positive axes and the graphs. So it's wanting us to find shaded region A plus shaded region B. And you know that the red linear function f of x is negative 8x plus 128. And then our other function g of x is x minus 16 quantity squared. So it's just a parabola shifted right 16 units. Now, whenever we're doing this, we have to realize that we cannot find region A and region B in the exact same integral. Region A, the top curve, is going to be f of x. The bottom curve is your x-axis, or y equals 0. region B, your top curve is not f of x, but g of x. So you'll see that's why whenever I worked this problem here, I had to attack it like this. And I'll go ahead and just bring this up and show more work for this one. I had to say, I'm going to find area A and area B separately and call that my total area. So the total area from 0 to 8. Now, where did I get 8? I had to find out when that linear function and when that quadratic function intersected. This one solved quite a bit easier. I didn't have to use a quadratic formula. I just solved it out factoring. Notice, when I set the linear function equal to the quadratic, that quadratic x minus 16 squared gives me x squared minus 32x plus 16 squared, which is 256. Now I got everything on the right-hand side, so I kept the x squared over there. Minus 32x plus 8x gave me minus 24x. 256 minus 128 gave me 128. I set that equal to 0. I found factors of 128 that sum to negative 24, and I found 16 and 8. I know 8 times 16 is 128. A negative 8 times a negative 16 is 128. But more importantly, a negative 8 plus a negative 16 sums to give me my negative 24 in the middle. So now it factors to this, and then I can say, well, then I know that these two functions are equal to one another at x equals 8 and at x equals 16. Now, you can see that in your picture. Here's the x equals 8. Here's the x equals 16. X equals 8 is the end of region A, where f of x is your top curve. And then x equals 8 to x equals 16, all in that region, you have g of x as your top function and the x-axis as your bottom function. So I say the total area from 0 to 8 is my linear function f of x integrated with respect to x. And again, you'd just be saying minus 0, y equals 0. The x-axis is your bottom function. And then from 8 to 16, g of x is your top function. You could have left it x minus 16 quantity squared inside there, or went ahead and squared it out like I did. Doesn't matter. Again, minus 0 for your bottom function, the x-axis, and that's from 8 to 16. So now we're just using the power rule on each one of these, understanding that you must keep them as two separate integrals. So the integral from 0 to 8, I'll have negative 4x squared plus 128x, evaluated from 0 to 8. Then I'll have x cubed over 3 minus 32x squared over 2 for minus 16x squared, plus 256x, integrated from 8 to 16. Now, I can say in this first one, the only thing that's going to have any relevance is the 8. Whenever you plug an 8 into that expression, you'll get a 768. In the second expression, both limits are going to have an answer. When I plugged a 16 into the 1/3 x cubed minus 16x squared plus 256x, I got the first fraction. And again, it's probably better if you'll keep it as a fraction. And then I knew I had to subtract the lower limit. When I plugged an 8 into that expression, I got the 3,584 over 3. So then I can say, well, it's the area I got from 0 to 8 plus the area that I had from 8 to 16. So 768 plus 512 over 3. Final answer of 2816 over 3. Now again, if you look at achieve, I think they're saying that they want an exact answer. So they wouldn't even want repeating decimal here. They want the fraction. So I'll say 2816 divided by 3. And that should represent the answer that they want there. I'll go up to check answer. And they like it. Now, the next few questions will take a serious step backwards in difficulty. Number 4. Let me show you this one. 4 gives me a linear function and a quadratic function again, and it's asking me to find the area between the two. All right, so instead of finding intersection points, I don't have to worry about that. I'm giving a beginning point and an ending point. If you graph these two functions out, 7x plus 8, linear function that starts at 8 has a slope of 7. You know it's going to end when x is 2, so that's 14 plus 8. It's going to end at 222. That'd be a very easy function to graph out. Your quadratic function is going to begin at x equals 2. When x is 2, it starts off at 2. We know it's going to be positive, kind of U-shaped here, but it doesn't get a chance to go up much, because when you plug a 2 into this, you'll just get 4 plus 4 plus 2. It's just going to go up to the ordered pair 210. Now the good news is that that tells you that this quadratic is the lower function or the bottom function throughout this entire interval from 0 to 2. So then I can say the area between the quadratic and the linear function is just going to be the top minus the bottom, 7x plus 8 minus the quadratic, x squared plus 2x plus 2. And that's going to be integrated from where the region begins to where it ends, 0 to 2. So then when I'm integrating from 0 to 2 of this simplified version, please notice I just went in here and said, well, the negative is going to distribute through this second group, and it's going to simplify to be minus x squared, 7x minus 2x plus 5x, 8 minus 2 plus 6. We use the power rule on each of those terms, and then we're integrating from 0 to 2. When you integrate a polynomial at 0, you get a 0. The only answer I need to worry about is when I plug in a 2. I get negative 8 over 3 plus 5 times 4. That's going to be 20 over 10 plus 12. Whenever you add those together, again, they're wanting fractional answers, 58 over 3. And I'll go ahead and put that in here, 58 over 3. Check that answer. Correct. Up next here, guys, for number 5. It's giving me the problem 11 sine x and 11 cosine x. My goal is to find the area between them on the interval 0 to pi. So I know that 11 times the sine and 11 times the cosine, that's just a magnitude or an amplitude change. It's going to magnify whatever the y value is. I know each of these would have a range from negative 11 to 11. But from 0 to pi, my sine function typically starts off at 0. It's going to go to 1 at pi over 2. Then it's going to go back down to 0 at pi. Well, this does the exact same thing, except it's going to reach a high point of 11 instead of 1. So I graphed out my sine function. My cosine function, I kind of graphed messily here. It looks more like a linear function the way I graphed it. The cosine, we know the cosine of 0 is 1. It's going to start off at 1, or in this case, 11. But it's going to arc downward in this. It doesn't go straight down like I do. It arcs downward. By the time it gets to pi over 2, it's at 0. And then it's going to keep on going downward to go to a negative 11 by the time it gets here. So my values are correct, just the shape of it's quite ugly in this. But now, here's the point that you needed to know. Well, we know that the sine and cosine have the exact same value. They're both the square root of 2 over 2 at pi over 4. So these two functions are going to intersect at pi over 4. After that, the cosine function's always beneath the sine function. Before pi over 4, the cosine function's on top. So if I want to find the area enclosed between these two curves, well, from 0 to pi over 4, it's the 11 cosine x minus the 11 sine x. You'll see that's what I did here. From pi over 4 to pi, your top function is the sine, the bottom is the cosine. So we had to set it up in that manner. Well, whenever we integrate cosine, we get sine. Whenever we integrate sine, we'll get the negative of the cosine. So a negative sine gives me a positive cosine there. So I end up with 11 sine x plus 11 cosine x evaluated from 0 to pi over 4. So I said, well, okay, I'm just going to factor that 11 out, and then I'll say, well, it's the top limit. If I plug in a pi over 4, sine of pi over 4 is the square root of 2 over 2. Cosine pi over 4, square root of 2 over 2. Well, what's the square root of 2 over 2 plus the square root of 2 over 2? It's the square root of 2. That's your upper limit. Now, minus your lower limit. Well, when you plug a 0 into this, the sine of 0 is 0, cosine of 0 is 1. That's where that -1 came from. And please keep in mind, I just went ahead and factored an 11 out of the expression and said it's going to be 11 times the upper limit minus the lower limit. Now I went on to the second one. The integral of sine is negative cosine. The integral of negative cosine is negative sine. So not surprisingly, oh, it's the same as the first group, just the opposite sign. Of course it's the opposite sign because we had to reverse the order of the multiple or the subtraction in the problem. So now whenever I'm evaluating that from pi over 4 to pi, well, the cosine of pi is -1. The sine of pi is 0. My upper limit is just a -1. Once again here, please notice what I've done, guys, is I factored that a -11 out front. And I said, well, it's going to be -11 times cosine of pi minus sine of pi. That gave me the -1. Now what happens when we evaluate at the lower limit of pi over 4? Well, you get minus the cosine of pi over 4. That's the negative square root of 2 over 2. Then you have another minus the square root of 2 over 2, minus the square root of 2 over 2, minus the square root of 2 over 2. That just gives me the minus the square root of 2. But then I can say, well, okay, I'll go ahead and subtract that in there. I'll get the negative square root of 2 for the lower limit. But now I need to make sure about that because, yes, that's right. It would be this minus the square root of 2 because it's minus the lower limit, and it'd be the square root of 2. So everything's correct here. Now when I try to simplify, though, I can say in the problem it told me decimal answers. I thought about putting a nice answer in terms of roots and radicals, but they don't want that. It says 3 decimal places, so I distributed the 11 in the first group and got this. Distributed the -11 in the second group and got this. Final answer of 31.113. We'll check that here. And they like it. It's rare that they give us a question where they want a decimal approximation. Typically, they want an exact answer. The next question here, and we have 2 quadratics. So this is one like we did in the notes for this section, to where we'll have to find where those 2 quadratics intersect. If we tried to find the area between 80 plus 4x minus 4x squared and the function 4x squared minus 20x. So you'll see, first thing I did, set them equal to one another. After you set them equal to one another, try to solve for x, obviously. I can't solve for x if I can't get a 0 on one side, so I moved everything to the left. I had negative 4x squared minus 4x squared minus 8x squared. 4x plus 20x is 24x, and then I already had my plus 80 set equal to 0. Now I looked at this and saw that, well, I could easily factor out a -8, and it should make it easier to factor. When I did, it was x squared minus 3x minus 10. So factors of -10 that sum to get to -3, -5, and +2. Factors to x minus 5, x plus 2, which means there's going to be solutions when x is equal to 5 and when x is equal to -2. That's when these 2 functions are equal to one another. Now, as soon as I knew that, I didn't even have to graph it out, and you don't have to either. But what I knew is that since one curve is a -4x squared, it has to be the top curve in this region. The other curve is a +4x squared. I knew g of x had to be the bottom function because it's a positive parabola. Please remember, every positive quadratic function in existence looks like a u. Every single negative quadratic in existence looks like an n. So at any time these are going to have an enclosed region of intersection, the negative parabola has to be the top function. It has to be. So I can say, okay, f of x is on top of g of x from -2 to 5. Let's find the area between there. I integrate from -2 to 5 of the function f of x minus the function g of x. Simplify that on the inside. Then I just use the power rule. 80x minus 12x to the second. This would be minus 8x cubed over 3, minus 8/3 x cubed. Evaluated from -2 to 5. So the first thing I did is I plugged a 5 into this expression, and I got my 1,100 divided by 3. Then I plugged a -2 into that expression and got the -272 over 3. Top limit minus the bottom limit gives me 1372 over 3. Now, please do keep in mind, whenever you're entering those in, it's so much easier if you'll just do it this way. 5 store x, and then you do the colon. Well, if it'll do the colon, there we go. Sorry, my calculator froze, guys. You're like, doesn't look so easy. It is easy, I promise. 5 store x, alpha decimal for the colon. Then you type in the expression, 80x plus 12x to the second. And then I'll say minus the fraction where I have 8x raised to the third, and we're dividing that by 3. So please notice 5 store into x into that gives me my upper limit. Then all you would have to do if you wanted the lower limit is hit second enter, bring this back in there and say, well, now we need to evaluate at -2. So negative, I'll insert in a 2, and you'll get your lower limit of the 272 over 3, or the -272 over 3. Makes it a lot easier. So now my final answer and the fractional answer that they want, 1372 over 3. We'll check that answer. Ajeeb likes it, as they better. Next question here. This one's wanting a decimal approximation. Okay, very easy problem. We know the larger the exponent of an exponential function, the more quickly it rises. So without even thinking about this one, if we're trying to find the area between e to the x and e to the 10x from 0 to 1, you know that the top function is e to the 10x and the bottom function is e to the x. Did you have to graph that one out to see that? No, I just did to try to be helpful. And the e to the 10x actually grows way more rapidly than what I have it shown here. But we'll say that this is okay for our problem. And we can say top function minus the bottom function from 0 to 1. Integrate that. Integral of any exponential function is that exponential function divided by the derivative of its exponent. So I get e to the 10x over 10. Integral of e to the x is just e to the x. Now we're evaluating that from 0 to 1. You don't really need a calculator, at least not for this part. When you plug in the 1, you'll get e to the 10 over 10 minus e to the first. That's what I got right there. That's the upper limit. Now we always subtract from that the lower limit. Well, the lower limit in this problem, you'd have e to the 0, which is 1 over 10, minus e to the 0, which is 1. So I have to worry about both of those terms in the lower limit. I'll get e to the 10th over 10 minus e, and then this would become minus a -9 over 10 or plus 9 over 10. We get our answer of 2,200.828. That answer should be great. We'll check that, and it is. Up next here, for number 8, now anytime it's asking you whether a region is vertically simple or horizontally simple, all it's referring to, if it's vertically simple, then it always has the same consistent top function and the same consistent bottom function. If it's horizontally simple, then there's always one curve that's always to the right of another curve. So we'll see. It says determine whether the regions bounded by the curves x is equal to y squared minus 6 and x is equal to 6 minus y squared is vertically simple or horizontally simple. Now, they don't graph it out for you, so you kind of have to think about that. I did that for you here. So if I graph out x is equal to y squared minus 6, that is a parabola pointing to the right, shifted backwards 6 units. So it's right here. So you say, well, it has an x-intercept at -6, positive y squared, so it points to the right. Well, what does 6 minus y squared mean? Well, that's a parabola that's going to point to the left that's been shifted 6 units to the right. So looks like that. Now, what I can see is that, is this region going to be vertically simple? No. Why not? Well, because from -6 to 6, there is not one consistent top function and one consistent low function. In this region, the top function is the y squared minus 6. In this region, the top function is the 6 minus y squared. So it is not vertically simple. Is it horizontally simple? And I'd say, yeah, because no matter where I go from the low point of intersection to the high point of intersection, the curve 6 minus y squared is always to the right in the enclosed region from the bottom y-intercept to the positive y or intersection. So I can say it's horizontally simple, but it is certainly not vertically simple. So I'll go into the problem and say, okay, let's answer that. The region is vertically simple. No, it is not. The region is horizontally simple. Yes. And check answer. Yes. For number 9, they're giving us a region that is vertically simple because I can immediately see, well, my red function is always on top of my blue function here. So this is going to be the more standard case of problem. Here's where I worked out this problem here. We're given x cubed minus 2x plus 9, and then 3x squared plus 13x minus 56. Okay, so I know that the quadratic function is the function on the bottom because it's the U-shaped function. I know that the cubic function is the function on the top. It has the 2 turning points. Okay, so now I already know without even any further thought that it's going to be the integral of the top minus the bottom. Now, of course, we're integrating that with respect to x, but we need to know where to start and end that integration, and I don't know that. So I have to go over here to the side and do some algebra, and I can say, so I need to find out when this cubic function is equal to that quadratic function. In order to do that, I get a side equal to 0. That's going to give me x cubed, and I would have minus 2x squared minus 3x squared for a minus 5x squared, minus 13x, then I would have plus 9 plus 56 for a total of plus 65. We set that equal to 0. Again, this is not one that it would be really nice to try to find out by hand. So instead of trying to factor that, no amount of, well, actually, factoring by grouping would actually work pretty easy there. I didn't. I used the cheapskate graphical analysis, but you could have factored by grouping there. Group the first 2 and group the second 2. You could factor out a 13 in the first one and x squared out of the first 2 terms. Factoring by grouping would work here. But what I did, and I'll go ahead and show you this because this is going to be more widely appropriate. Factoring by grouping typically does not work in these problems. But what you can do, if it ever has a rational root, and in order to determine if it has a rational root, the easiest thing to do is to just go ahead and graph it. So I'll graph that out, put a 0 in y2. Typically our roots are between -10 and 10, so I'll look at this. And I can immediately see, oh, okay, it has 3 solutions. I expected it to have 3 solutions. I can already see the first solution is going to be useless. It's not going to be a whole number. Same thing with the second one, but it looks like that third one's might give me a nice answer. So I'll go second count 5, enter. When it says guess, I'll arrow over to where that third solution is, and I'll say, tell me what that one is. And it's 5. Now, I guarantee if you'd went to the others, you get irrational answers. I wouldn't know what to make of those yet. So I take the answer that I know I have and say, well, I know x equals 5 is a solution to this curve, which means x minus 5 is a root. You could either use long division with x minus 5, or I'll synthetically divide with the solution 5. Synthetically divide into the coefficients of 1, -5, -13, and 65. We remember when we use synthetic division, you bring the first term down. 5 times 1 is 5. Add the next 2. Well, you get a 0. 5 times 0 is 0. Add these 2. -13 plus 0 is -13. 5 times -13 is -65. No surprise, and we expected a remainder of 0. You get a remainder of 0. That's just showing that, yes, that was a solution. So now what I know, f of x is factorable. If x equals 5 is a solution, then x minus 5 is a factor. The other factor has to be 1 power lower, so it's going to be 1x squared plus 0x minus 13. Well, it's x squared minus 13. Clearly, if you set the first factor equal to 0, you get your 5 that we already knew that we had. Set your second factor equal to 0, and you'll get the positive and negative root of 13. Now, the region in our picture, that's just the region between the negative and positive root of 13. Please notice in the picture how it's equidistant from the y-axis in each direction, so it has to be the negative and positive root of 13. So I'll say, okay, yes, they are going to intersect again later on, but that's not relevant for the area that we're interested in. We'll integrate from the negative root of 13 to the positive root of 13 at the top minus the bottom. I just simplified that top minus the bottom here, and then I used the power rule to integrate each of those terms. And then I'm evaluating from the negative root of 13 to the positive root of 13. This is not a problem where you can depend upon your calculator to give you a decimal answer. It wants an exact answer. So what I did here when I plugged the root of 13 in, well, I knew that the root of 13 to the 4th power, that's the same thing as 13 squared. Well, 13 squared is 169. First term's 169 over 4. Now minus 5 times the root of 13 cubed. Well, that's the root of 13 times the root of 13, which is 13. 13 times 5 is 65. But then you have times a third root of 13. So I have minus 65 on the root of 13 over 3. Your next term, you'd have the root of 13 squared. That's 13. 13 times 13, 169. You have your 169 over 2. Your last term, of course, you'll have plus 65 on the root of 13. All of this is the upper limit. We subtract from that the lower limit when you evaluate this expression at the negative root of 13. Well, that first term, if you have negative the root of 13 to the 4th power, you're going to have the negative raised to a 4th, which is obviously a positive, but then the root of 13 to the 4th, that's the same thing as 13 to the 2nd power, 169. You've got your 169 over 4 again. Your next term, it's automatically going to be a positive because the negative raised to an odd is a negative, but then a negative times a negative is a positive. And then I can say, well, the root of 13 cubed, that's going to be 13 times the root of 13. The 13 whole number multiplies the 5, gives me 65 on the root of 13 over a denominator of 3. My next term, it's going to stay negative because I know that the negative root of 13 squared is just going to be 13. 13 times 13, 169. Still a minus out in front, minus 169 over 2. Your last term, it is going to change the sign because you'll have 65 times a negative 1 on the root of 13 makes it minus 65 on the root of 13. Now we say upper limit minus lower limit. Some of this does cancel out. The 169 over 4 minus 169 over 4 cancels. We have the negative 169 over 2 minus a negative 169 over 2. Those cancel. But what doesn't cancel is we'll have a negative 65 on the root of 13 over 3 minus a 65 on the root of 13 over 3. That's giving me negative 130 on the root of 13 over 3. And then I'll have plus 65 on the root of 13 plus 65 on the root of 13. That's plus 130 on the root of 13. I just went ahead and got a common denominator here, guys. I just said, well, this has a denominator of 3, so all I have to do is call this 390 on the root of 13 over 3. It's the same thing as 130 on the root of 13. Now that I have a common denominator, I can combine my numerators. 390 minus 130 is 260 on the root of 13 over 3. This problem had some really cool arithmetic in it. I love stuff like that. So final answer here, we'll say 260 on the root of 13 over 3. 260 square root of 13. All that's divided by 3. We'll check that answer. They wanted an exact answer. Yes. Up next here for number 10. The work I did for that, let me show that a bit more here. Let's see, there we go. So for number 10, I'll just maximize my screen. That'll show it better. For number 10, we had x is equal to sine of 8y, and then x is equal to 1 minus the cosine of 8y. Well, throughout this curve, I know that the sine function is always on top of the cosine function. And please keep in mind, or sorry, not top, to the right. So the red curve is always to the right of the blue curve in this region. So I can say, well, since I know it's always to the right, it's always going to be right minus the left here. So right minus the left, and this is from 0 to pi over 16. Well, okay, when I distributed that negative throughout that, I just got minus 1, and then, of course, plus the cosine of 8y. Then I integrated. The integral of the sine of 8y, please be careful with that. You can say, well, I know that the integral of the sine is the negative cosine of 8y, but then you have to divide by the derivative of the angle, divided by 8. Second term is just power rule. The integral of minus 1y to the 0 is minus 1y to the first. And then we'll say the last term, the integral of the cosine of 8y is the sine of 8y divided by the derivative of that angle divided by 8. We get our integral answer here. We're having to evaluate that from 0 to pi over 16. When you plug the pi over 16 in, 8 times pi over 16, it's just going to give you pi over 2. I know that the cosine of pi over 2 is 0, so you'll see that's where that term came from, minus pi over 16. The sine of pi over 16 times 8 is going to be the sine of pi over 2. That's 1 over 8. So then I can say, okay, I've got my upper limit done. What about the lower limit? Minus, when I plug a 0 into the first term, cosine of 0 is 1. This is going to give me a negative 1. I'll have over 8. The next two terms, 0, and then the sine of 0 is 0, so the next two terms are both 0. So I get a negative 1 over 8 for my lower limit, but I know I need to subtract it. So I'll get negative pi over 16 plus 1 over 8 plus 1 over 8, that's plus 2 over 8 or 1/4 minus the pi over 16. I think I'll just put my answer as that and say the 1 over 4, and then we have minus pi, which I'll use their palette for that, divided by 16 should be what they want there. And it is. For the next one here, it's giving me or asking me to find the area between the region lying to the right of x is equal to y squared plus 12y plus 18, and to the left of y equals 5y plus 6. So here's the work I did for that. They've already told us which function is the right-hand function and the left-hand function. They said the area is to the left of this function and to the right of this function. So you know the x equals 5y plus 6 is the right-hand function in this problem. So I can say, well, it's the right minus the left, and I need to put this in terms of y. So 5y plus 6 minus y squared plus 12y plus 18. Right minus left. And this has to be from where the region starts to where the region ends. So you'll see I had to do that over here. And I set one curve equal to the other curve and tried to solve for the values of y that satisfied this. I had y squared plus 12y, had to subtract 5y on both sides for plus 7y. I had plus 18 minus 6 gives me plus 12. Factors of 12 that sum to get to 7, well, 4 and 3, y plus 4, y plus 3. So this means that the points of intersection here are at -3 and at -4. So you always want to go from low to high. So I had to integrate here, and I first made a mistake and integrated from -3 to 4. I had to white it out. The low y value is -4, so we're integrating from -4 up to -3 of the right minus the left. I simplified that inside function to -y squared, and then it was minus 7y, 6 minus 18, -12. Integrated that from -4 to 3. Power rule told me that this was -y cubed over 3 minus 7y squared over 2. minus 12y. When we evaluate that from -4 to -3, I plugged in a -3 into this expression, and when I did that, I got the 27/2. Then when I plugged in the -4, I guarantee you I got an answer of -40/3, or sorry, positive 40/3. And I said it's the upper limit minus the lower limit. So 27/2 minus the lower limit of 40/3 when I plugged in the -4. And I got a final answer of just 1/6 here. So that should be the answer that Achieve is looking for. When I try checking that out here, 1/6, check answer. Gorgeous. All right, guys. So for the rest of the problems in this section, I'll do another video. I don't want to make these videos too long, but hopefully you're following along pretty well in this section. Let me know if you have any questions. I'll be glad to help.